So let's go. So a bit introduction, but Christian has already said many things. So basically, I am working for several years now on how to adapt program analysis techniques, which have, and especially formal methods, which has been designed in the context of safety analysis and source level analysis to the case of binary level security analysis. So what the talk is about? So first, it's about symbolic execution because it's formal and it works. And yeah, the thing is, if you look at symbolic execution, so it originates from people who are coming from safety, testing, and these kind of things. But very quickly, it gets adopted by security people, notably David Bromley introduced symbolic execution into the security field. And I mean, it works. If you could find some buffer overflow, that's a software engineering issue, that's a safety issue, and that's a security issue anyway. But the question is there some difference between this code level safety analysis and code level security? So sure, you can use symbolic execution for security by just taking it as it is, but can we see other new challenge in the security context? How is it different or not? How is it more difficult or not? And how can we adapt or not symbolic execution format? So this talk is a kind of reflection of some work we have been doing in my team in the previous years. So it's not intended to be very technical, it's more an overview. So do not hesitate to ask questions at some point. And of course, I am available more face-to-face if you want more technical details. And I didn't do this work alone, so it's teamwork since some while now with many students and collaborators. Some of the students are here now and they're not students anymore. It's nice to see them. Okay, so first question, why do we want to work on binary code? Seems to be complicated, so do we have some good reasons for that? Actually, there are many good reasons for that. I would even say that usually the source level scenario where you get all the source code actually often almost never happen in practice. So when we want to go to binary code, so many times in a company, you build some of the source code, but not all. You use also third-party component and these kind of things. So for this component, if you want to have some insurance about them, you only have a binary code. Then you have also the scenario of post-compilation verification in some way. Maybe you have done some nice analysis on your source, but then it gets compiled. And what is really executed is this executable code actually. And maybe the compiler introduced some bug or remove some protection or whatever. So maybe you want also to use binary level in analysis in complement to source level analysis. This goes in some way with protection evaluation, where for some kind of protection, you really put them on the binary code. It doesn't really mean anything at the source code, and so you want to evaluate them. You have also, of course, the scenario of malware comprehension and malware detection, because in that case, obviously, you don't have the source code. And in some case, you want to go even lower than the binary code in some way and really wants to look at some micro-architectural details, like in the recent micro-architectural attacks such as Spectre or Meltdown. So this is kind of a scenario we are exploring. Just one example of this idea of why do we really need, even when we have the source, it can be useful to check the binary. So this is kind of an old example, but kind of typical. So for people who are not aware of it, that can be interesting. So that's a security issue. So here at some point, you have some function and you have some local buffer. You will copy the password in clear text, make some work about it. And then since it's some sensitive information, once you have done your work, you will just erase it so that the password value is no more in the memory. So what's the goal of that? Because from a C point of view, there is no real problem. Because anyway, once you exit the function, the local buffer shouldn't really exist anymore. So there is no problem. The problem is if at some point later in the execution, you have an attack, like a memory overflow or something like that. Oh, sorry. Then if the password value was in the stack, then you could go back to the stack address and read it and get the value. So you must clear this value. This is secret erasure, and this is a common security policy. So your source is good, perfect. But then now what will do any naive compiler? It will see that basically you are putting some value inside a location which is no more accessible. So this is completely useless, right? And so any diffuse optimization will just remove it. So your source is valid, but when you look at the assembly code or binary code, you don't have this secret erasure anymore. So you may have, in some way, your executable is more vulnerable than your source was. So obviously, you have ways of doing that in compiler. You could put some volatile pragma or these kind of things to help remove that. But it's just to show that actually it's important to look at binary code. And also another point is that security properties are different than safety properties. So it's not really a compiler bug. The problem is that compilers are designed to keep the input-output relationship. And this is not a question of input-output relationship. So it's certainly not what the developer wanted to have, but it's not really a compiler bug. So it's all the more difficult to get rid of. Hence the need for binary code analysis in some setting. Okay. So then usually in this talk, I give some background about symbolic execution. But we already know it that. I'm sure everybody knows about it. Okay. So now we have seen that it's important to be able to go to binary code, to binary level. But what is different in our binary level security analysis setting? I think there are three different ways. So first, we have some binary code, and I will explain a little bit why it is more complicated than source level code. Then we have some attacker, which can be taken into account in some scenario. And also the security property we want to look at may be different. So for this part, I will just explain hereafter, okay? For this part, it will be more on the case study and example I will show. I will give you some example on how it can affect the standard program analysis. Okay, so the main problem with binary code analysis is that binary code lacks structure. So first of all, you don't really know. So what usually you get is some big blob of instruction. You know the starting point and you know the architecture. Sometimes you don't even know the architecture, but then it's a problem. So for example, you don't really know initially where the instructions are. You don't really know the control flow, so the edge between the different instructions. And you also don't really know the memory structure. So typically, what is the stack, what is the heap, and this kind of thing. So there are different scenarios here, obviously, because, for example, you could say, okay, let us use a disassembler. And indeed, disassembler like IDA Pro, in many cases, with a nice program compiled by a nice compiler, they will recover some very decent approximation. So if you want to do some exploration, why not? Then if you want to claim formal verification, that would be more a problem because it will be up to the quality of what is output by this disassembler. And if you consider obfuscated program, then this disassembler won't work anymore. Yeah, so just to give you an idea, so regarding control flow graph, why is it so hard? So what happened in assembly level? So usually you know the current address, okay? And so at this address, you can go into the memory, look at the code, and from the manual, Intel manual, ARM manual, so you know what instruction you have. Okay, this may be a bit difficult to decode, but this is just a huge finite state machine, no problem. And with this instruction, usually you know the potential successor. So if you have some addition, let's say, then you know that the successor is just after the current address plus the size of your instruction plus 1. Okay. If you have some jump instruction with a static address, like jump to address 1000, then you know that the next instruction will be at address 1000. So far, so good, it's very easy. You have only one difficulty, but it makes all the thing difficult, is what we call dynamic jump, which is of the form jump to the value which is in register EAX, for example. Then if you want to know where the next instruction is, you need to know the value of EAX. But to know the value of EAX, then you need some static analysis. And for that, you need a CFG. And yeah, you have a cycle here because, and usually in standard program analysis, there is a kind of hidden hypothesis. It's so implicit that nobody just talked about it. It is that it's pretty easy to get a decent approximation of a controlled flow graph. And then you perform your analysis on it. At binary level, you don't have that. It's probably as hard, recovering the CFG is probably as hard as performing the analysis, and recovering a precise CFG may be even harder than most of the analysis anyway. So that's really a problem. You must do your value analysis and your CFG recovery at the same time. So typically for symbolic execution, it will be okay, but for abstract interpretation, that's really a nightmare at binary level. So another problem is the lack of structure also in the memory. So what happens usually in source level analysis is that your memory is made of several regions which are implicitly separated actually. So for example, in C, people tend to take the on-CC semantic. And so you will consider that basically every local variable are separated from each other. And for example, you cannot start from one local variable, overflow it, and then arrive in another one. It's considered illegal. Even if in the stack they will probably be sequentially put, you don't have the right to make this assumption. And obviously different calls to malloc leads to new region and so on. So the big advantage when you do some analysis is that imagine that at some point, you know that you are reading in some of this region, but you don't really know where. Then you will have to update the information you have, but you will have only to update this particular region. So maybe you lose all information on this one, malloc one, but the other ones stay the same. But now in binary code, you don't have this a priori separation. So you just have one big thing. So if at some point you have some right, and you don't really know where, then basically you trash your whole memory and your analysis finish. So that's also a bit different. So again, there are two different stories here. So for symbolic execution, that's not that complicated because you can use arrays, the theory of arrays. So obviously you will have one big array with many write and read. That's not the best case. But yeah, solver, you can use concretization, some solver can do some things. In abstract interpretation, it means that you must be rather precise on any write, which is obviously difficult. So you have also other problems, but that's the main two. Okay, so now just a few words about BinSec, and after we go into these shades, by the way. Let's see if we have 4 or 5, maybe more, I don't know. So what is BinSec? So BinSec is a prototype platform. It's a binary level program analyzer. So that BinSec follow kind of a standard architecture in the field, actually. So you have some intermediate representation, which is intended to be small, very clear, concise, and easy to work with. So from this intermediate representation, you will build some decoder from normal, from existing architecture instruction set. So typically x86, ARM, and so on. So this work is a bit painful to do, actually. So just to give you an idea, typically the x86 manual, you have hundreds of instructions. All of them are very complicated with side effects and so on. So you really need to be used to that to reason about it. Once you get into the intermediate representation, you have only 5 or 6 class of instructions, so it's much easier. Then we have mostly a symbolic execution engine. We have also some work on static analysis. So especially last year, we had some nice results about formal verification of embedded system, but it's more complicated to do it generically. And what the kind of problem we are looking at in the team are advanced reverse problem and obfuscation, vulnerability analysis, binary level security proof. We have also done some work on automatic lifting of inline assembly code and this kind of thing. Basically, every time it's low level and it sounds fun, I will try to apply it. Okay, so just a few words because I had a question yesterday about that, so about the intermediate representation we are using. So it's actually the good thing with binary code analysis is that the semantic is pretty simple, and the intermediate we are in sequential mode actually. So what we are using, basically, we have some assignment, some static jump, some dynamic jump, and some conditionals. And regarding operators, we can obviously load and read value in memory. We have all the bitwise, logical bitwise operation, and we have modular arithmetic operation. So we don't handle floating point, actually. So this is pretty easy to work with representation. So this is pretty similar to what can be found in BAP, which I know well. I guess Montico is probably a bit. I know you said you don't have intermediate representation. Yeah, okay, but you know, I think Triton looks the same as well. So this is pretty standard in the field, I guess now. Just to give you an idea, for people not used to x86, so this is okay, some opcode. Then going to the manual, you will see that it corresponds to some addition. Basically, in ABX, you will put the addition of ABX plus some constants. And now it is how it is translated in our systems, because you can see that indeed there is the addition, okay, as expected. So yeah, one is in exile. And then we put it into some temporary variable and then put it in ABX. And then you have also lots of side effects, which are in x86, mostly any instruction updates some flags. So this one say that whether the addition has some overflow or not, whether the result is positive or not, whether the result is 0 or not, and some other things. So for any small instruction from your assembly code, you have many more instructions on binary code. So that's another difficulty. Usually binary code is much bigger and verbose than source level. Okay, and we use symbolic execution. So why is it nice on the binary analysis setting? Because if you step back, I think the first time I heard about program analysis on binary code at a formal method conference was by Thomas Rebs, actually, in 2004, I guess. It was about a static analysis, and it's a VSA paper. But then it turns out that it's very difficult to make it work. And then in 2008, there was some work by Patrice Godefroy, actually. And we did it in parallel, so etc. And we both realized that actually adapting symbolic execution was much easier. First, in symbolic execution, you don't need the CFG, actually. You just crawl it and you discover it on the fly. So it's very easy. Then you don't have this problem of dynamic jump. Basically, every time you hit a dynamic jump, so you have your path predicate and you have your jump, and you know that you are jumping on value of variable AX. So you can ask the solver to solve the predicate and to give you a value for AX. So it will give you a target. And then you can iterate and ask the solver for new value. And so you will find all the dynamic jump, dynamic targets suitable for your path. So this way you can just discover the CFG incrementally. Obviously, you are not, maybe you will not find everything, but anyway, that's a general problem of symbolic execution. You are never sure to explore everything. And regarding the memory, as I already said, using SMT solver with bit vectors and arrays helps. Obviously, you can't handle a long chains of symbolic write and reads, but you can already do things, especially with concretization. Okay, so now let's go to the real meat of the talk. So how can we use symbolic execution for security? So there is obviously the standard usage, and then I will show you a bit of refinement. So first, if you just take symbolic execution, you send it on a binary code, then you can just explore the binary code, and then you get a test suite with intensive path exploration. So this is well known now as white box fuzzing, smart fuzzing, whatever you want. And the point is, okay, it takes resource to get one input, but you are ensured that every input explores a new path. And you can go obviously a bit better, because every time you have some potential bug, like a pointer dereference and so on, then you can add an extra check. And then if you get an input, it's an input, then you are sure that to trigger a bug. Okay, perfect. And you can even go a bit further. in security. So this is work which has been pioneered by Sean Elan in his master's thesis, and then a few years later, done by David Bramley, and now it's a whole field which is called automatic exploit generation. So let us now imagine that you have a path, and at some point, instead of just saying, okay, try to find me some input which write beyond the bound of the current region, you can directly ask, okay, find me an input which do some overflow, and then in the stack I want to write these bytes, which will correspond to some shell code. And then also I want to rewrite also the stack pointer so that at the next return I will point into the code I just injected. And if a solver gives you a model, basically what you get is some input which really makes some basic overflow attacks, where you will really have the overflow, or follow the path, have the overflow, rewrite the stack with the code you want, and then at the next return, then since you have also rewritten your return address, you will jump into the code. So this is the basic overflow exploitation, but you can do that. And then there have been lots of work with that on symbolic execution, so now obviously you have some protection, so you cannot put your exploit directly in the stack. So you have some work to create what people in security call ROB attacks, so return-oriented programming. And you can use a symbolic execution like technique to help you for that, and also some for other form of exploitation. Okay, but I won't go into the detail. I don't work in this field actually, but it's interesting to see how the basic techniques can be already used almost as it is for this kind of application. Just a small interesting thing. Obviously, in this field, the main problem is scalability, because you have many paths to explore. And if you start considering bugs which are a bit complicated, like use after free, where you are looking for sequence of bugs, it's even worse for symbolic execution, because you are not looking for one path which arrives at some particular location. You are really trying to have some sequence of events. So some work we did some time ago with Jocelyn Fest, with now Trail of Bit, was I think working on Manticore, or at least around Manticore. Yeah, let's say, and Robin. So what we did was pretty interesting. Jocelyn came up with a static analysis for detecting potential use after free on binary code. And then basically we're combining it with symbolic execution. So you had first some static analysis to detect potential problem, and then some symbolic execution to try to trigger the problem. What is interesting here is that I tell you that static analysis was a nightmare on binary code. That's right if you want to be sound. But in that case, what we want in the end is some bug. So what we had, but basically that the analysis, static analysis itself was never sound nor complete. So it could miss bug. And also it could give you false alarm. But in the end, what it gave you was this kind of things that Jocelyn called slice, or basically it tells you that if you stay in this area and eat this free, and then stay in this area and eat this use, then maybe you have a use after free. And then you give that to the symbolic execution and you use it to target, to tailor its exploration. So obviously, if the slice is too big, you don't have any advantage. But if the slice is precise enough, then you can speed up symbolic execution a lot. That's an interesting way to combine one technique, which is correct in the sense of symbolic execution, and one technique which isn't sound, and you combine them, and in the end, you can find real bugs. Okay, so now let's go for less exotic usage of symbolic execution. So first case, robust execution. So one thing you discover when you talk with people in security is that some bugs are more important than the other. So we are used in France to work with a very highly regulated safety critical system. So in this system, any bug is a problem and you have to fix it. And if you report some bug to some big open source project, some in non-regulated field anyway, most of the time, the first question will be, okay, but is it an important bug or not? And Basically, they have thousands of bugs which are not fixed. And the question is, why should they fix your bug and not one of the 101 or 1001 they are in their backlog? And usually the underlying question is, okay, is it a real security problem or not, or is it just a mere bug? So you start having some interesting distinction here. So one idea we have is, okay, how could we, because this is one problem with fuzzing and symbolic execution. The tools now are very good at finding many bugs. But if you find, I think Andreas Zeller had some time at a paper on Firefox where we're finding like 4,000 or 5,000 bugs in Firefox. And then you give the 5,000 bugs to the guy, what can they do? And just, anyway, they can fix 100. So how do they do? So we try to think a bit about that. And in this line of work, we propose what we call robust reachability and robust symbolic execution. So this is work which has been done by Guillaume Gérol, who is about to finish his PhD, and Benjamin Farinier, who is now at TU Vienne. So it comes down to this, the way we attack this problem is that to realize that in practice, standard symbolic reasoning may produce false positive, which is a bit counterintuitive because usually we say, okay, but with symbolic execution, we cannot find everything, but when we find something, that's a real bug. Actually, that's a real bug if you consider standard reachability, but in practice, here is what can happen. So let us imagine this very simple program here. So here you have some input, and here you have something which is more like some input from the environment. It's something you cannot control, it's random, okay? And then after you want to arrive here. So if you do some symbolic execution, then you will have to solve this, and then probably the solver will give you some answer. So let us imagine it will return that. Oh, sorry, okay. And then symbolic execution will tell you, okay, very easy, just put A minus 100, B equals to 10, or X equal to 0. And then if you try to replay it, obviously X will change to the left execution because you cannot control it. And then with that, you will just end up somewhere else. So from reachability point of view, it's not a false positive, but in practice it is. And actually, this kind of problem happens a lot on binary code analysis. So let us imagine you have some overflow, and your program has some canary. And then you want to bypass the canary and rewrite something. And what happens usually, and you want obviously to not trigger the canary. So if you just ask the symbolic execution, usually what will happen is that the symbolic execution will tell you, oh, the program is vulnerable, it's very easy, you put this input, and then obviously when you have to rewrite the canary, just take the value of the canary, that's very easy. But yeah, you cannot do that, you don't know the value of the canary. And you have also some problem, like on some example, you may think your technique is able to invert crypto, but actually just suppose that the value of the hash is just in the uninitialized memory or something like that. So it happens a lot, actually. So what do we propose for that? So I don't say that we tackle the big problem of knowing what is an interesting bug or not, but at least we propose one thing. So we propose robust reachability, where the idea is to give a partition of input between what you control, or the attacker control, and what you cannot control. And then in reachability, usually you want just, so A is what you control, X is what you do not control. You just want some value of A and X to reach the location you want, whatever you want. So now we want to find an input we control, so that whatever the environment does, we will indeed reach our goal. So intuitively, it means that it is a bug or an attack or whatever that the attacker can trigger with 100% reliability independently of the rest of the world. So this is obviously much more dangerous than something that depends a lot on external action. So yeah, okay. So how can we solve that in practice? So we have tried it. So it turns out that now, yeah, because there is a quantifier, so it's not very cool. For a long time, SMT solvers were not able to generate models when there was quantifiers. So now they are. So it turns out that, okay, obviously you have some overhead, but it works not too badly actually. We are a bit surprised. So on some example, basically when it works, there is mostly no overhead compared to standard queries and symbolic execution, but sometimes you get into some timeout because then just the solver gets lost. So this is if you just want to use SMT solver as they are. Also another problem is that some SMT solver which are very good for bit vectors and array do not have quantification, for example. So typically it's better to use it free in this case because it has good support for quantifiers. Or maybe just another thing, I will come back to that later. At KLEE, we also propose another way of dealing with this kind of queries, which is basically a reduction to the quantifier-free case. So basically, we take the formula with some quantifiers, and we want a model. And so we'll create a formula which is quantifier-free. And if we are able to find a model on this formula, then we are able to find a model for the quantified formula. But this is not, the approach is not complete, so it can happen that we are not able to find a model with our technique while actually it exists. So that's another way of doing this kind of problems. So just to give you a few examples. So for example, so we set up some example with control value and uncontrolled value. So here you have, so symbolic execution and robust symbolic execution and robust symbolic execution with path merging. So you can see that standard symbolic execution on this example will create many false positives actually. So that's a problem because it is exactly what we want to avoid. So 30 of them are indeed reachable, but 16 are not robustly reachable and they are reported as reachable. And for robust symbolic execution, we'll get better answer and no false positive, which is good, but we have also some inconclusive verdict and some timeout. And then if we had path merging on this example, we are much better. Actually, that's pretty interesting here because path merging gives you more expressive power. It is required in the case of robustness. And we have also some studies. Basically, we took some real CVE to see what happened, and for some of them, we are indeed able to check that they were not only reachable, they were robustly reachable, which show how dangerous they are. And so, for example, also in this one, if we don't put the stack canary, we can show that it is robustly reachable, and if we had the stack canary, we time out. So it would have been better to prove that it was not reachable anymore, but it's kind of give you some hint that something is happened and that the technique indeed makes a difference. Because if it has been only symbolic execution, then just stack canary are easy to bypass. Okay. So that was the problem of some bugs matters than some others. Okay. Now, it also happens in security that you are not interested only in safety, but in more complicated properties. So especially what we call hyper properties or leakage. So if you consider the problem of cryptographic primitive or these kind of things, so some powerful attacks are what we call side channel attacks. So basically, you don't try to attack the cryptography by itself. The mathematical aspect is too strong. But what can happen is that, for example, if the execution time depends on your secret input, and you know it, then you can, maybe it depends only for some adequate public input, then you can give this public input, just watch for the timing, and depending on the timing, then you know which secret input has been used. And this is for timing attack, but you have also cache attack and this kind of things. And the point is here, you are not looking for one execution which one point, you are looking for pairs of execution which have the same public input and which have different secret and which make a different, some observable difference. So what we will use here is relational symbolic execution. So basically we are now you kind of adapt symbolic execution, and instead of following only one path, you follow pairs of paths actually. But since it is what we call constant time property, so this is a difference against this timing channel attacks, where you ask basically that if you have two inputs at the same public part, they must follow the same, they must make the same decision on the branch, and they must have the same memory access. So what we do basically, we follow two executions, but which sharing the same path. And then at each branch and each memory access, we ask to the solver, okay, is it possible to find some input where the public input are the same, the private input are different, and indeed, for this branch, it will make a different decision, or for this memory access, it will make a difference. So if the solver answers yes, then you get an attack for this constant time model, and this is a problem. And if you explored everything and the solver say no, then you don't have any problem regarding this timing attack. The question we have here from symbolic execution point of view are first that you are adding lots of extra queries, so you will have exploration as usual, but then at every memory access you will add queries. Is there any problem and so on? So at some point it costs a lot. And also you have a question of how you handle this new kind of path predicate, which are basically bigger because you have two formula. The kind of techniques we are using, actually we use some techniques from Christian, from Shadow of Hadoop, for having the complicated path predicate, because most of the predicate are shared. So we use some representation to take that into account. And then we have also some propagation information along the path predicate to get rid of most of the insecurity query as soon as we can. So with using all of that, we managed to have something very usable on the standard cryptographic primitive, actually. So yeah, we study a lot of crypto primitive implementation, and we find a few fun facts. So for example, we have example where the code is proved correct on LLVM level, and then we can find bugs at the binary level. So it was well known from source to binary, but even LLVM is not enough in some way. And we have also a funny example where the LLVM code has some problem, but once it is compiled, there is no problem anymore, which is lucky, but okay. So now, untitled symbolic execution. The question is now, okay, we are still in this cryptographic primitive. And but the problem is that we want to take speculation into account. So, and roughly, it means that the attacker can now observe more behavior than we could expect. He has the right to take into account this speculation. So what are speculation? In processor, basically, you will the processor will speculate on some decision like branch or memory access, so that it can continue computing instead of waiting for something. And it turns out that this kind of thing, so if the choice is the good one, then they continue, and if it's not the good one, it should be rolled back, but it happens that everything is not rolled back, and there are still some side effect, and then some attacker can take advantage of it. What does it mean from a symbolic execution point of view? It looks like a bit the previous scenario, but now you have much, much more behavior actually. So for example, from speculation on branch, it means that whatever your value, you can take the true branch or the fast branch. For memory access, it means also that whatever your real address, you don't care because you can have speculation which say that, okay, don't look at the first address in memory, look at the previous one or this kind of thing. So you have a huge path explosion. So for example, for a problem with a sequential semantic, you have 14 paths. In speculative semantic, you have 37 million paths. So it's really an awful explosion. So this is only a problem of timing the explosion from this speculative operation, but you really need to do it, otherwise you are dead. So basically what we did, we considered two sorts of speculation, memory and branches, and we come up with smart encoding of speculation. In some way, you can see it as a dedicated merge for some particular case of path explosion and targeted simplification. yeah, and for example, we discover some fun fact, like, so you have software protection, which have been proposed against for the case of branch speculation. It turns out that this kind of protection are very vulnerable to memory-based speculation, so, which is kind of annoying. Yeah, time is running. So for this one, I will be very quick. So one thing, usually in symbolic execution, you want to get one solution for one path. But further, they have shown us that having lots of solutions is very nice. So it would be interesting to be able to enumerate quickly on this kind of problem. But SMT solvers are not very good at enumerating because basically they just resolve. So we propose something which is more integrated. So this is still work in progress, and we have a poster on it. So you can discuss on that. And a little bonus, because we have talked about backward, Jan told us about backward symbolic execution yesterday. So in the case of security, it can be also very, very interesting. So let us see an example. So and it's also an interesting case where sometimes the code itself is adversarial in the sense it has been designed to be hard to analyze. So this is the problem of deobfuscation. Robin told us a little bit yesterday. So what you can do with this backward bounded analysis, so you will go backward, but only up to a given bound, is that with that, you can really show that some predicate is not feasible. And then it's very interesting because one common obfuscation scenario is indeed that you had some fake branch, which are not this feasible, but the developer know it, but not the attacker. And then beyond this branch, you had lots of useless code, junk code, so that you just lose the analyst or the analyzer. And with this kind of local backward bounded symbolic execution, you can perform this kind of check very, very, very efficiently because it's only local, so it's very scalable. So just to give you some ideas, we apply it to some pretty big code actually. And at the time, we did the whole analysis in 3 hours, and now it runs in 12 minutes. So you really work predicate by predicate. Okay, so this is the end of my talk, a bit late, but we are arriving. So the main message is that safety is not security, and that if you really want to look at security problems and see what is original in them, you have lots of new fun problems for program analysis, symbolic execution. So you have the problem of binary code itself, but you have also the problem of the attacker. In some scenario, maybe he has some extraction, maybe he can change the code so that the code is difficult to analyze. And you have also different properties, like typically hyper properties, so this kind of leakage. But you have also probably you could have some application of some quantitative measure and these kind of things. And you have also, generally speaking, the question of what are the important bugs. And ideally, we would like the analysis to search only for the important bugs and just do not consider the others. Yeah. So maybe a last thing. So symbolic execution turns out to be very flexible, actually. So if you adapt it a bit, you can handle many, many situations. Most of the time, you still have to really optimize it for your problems. And yeah, that's really interesting direction, and there are still many exciting challenges. And yeah, by the way, we are hiring. We have many projects which are starting, so we have many open positions or postdoc and PhD. Thank you.